Hi. So midterms will be returned Monday, if you didn't know that. We are, I don't know, maybe overall maybe roughly halfway done with grading, or maybe a little more than halfway. So yeah, you're getting back on Monday, and I don't have any numbers to tell you or anything like that about how things are going. But you'll get summary statistics on Monday. Basically, I'll just give you a brief overview of what the summary statistics will mean. Average in SD, sort of standard summary statistics. For midterms, I think it's nice for you to have the 80th percentile, the 50th percentile, and the 10th percentile. The reason why is that the way the curve works is that at the end of the semester, the top 20% of the class roughly gets A's, some kind of an A. And so if you're above the 80th percentile in the midterm, that sort of says you're kind of on track to get some kind of an A. If you're between the 80th and the 50th, that 30%, some kind of a B, and then 40% C. So between the 10th and the 50th percentile, some kind of a C. Below the 10th percentile, probably want to do better on the final to pass the class. So that's roughly what those percentiles mean. It's not like an average of your letter grades or anything. Like your final grade will be a total of all the points weighted appropriately, and everyone's ranked by that. So if you get like half your grade is an A, half the grade is I don't know, maybe one way to think of it is if half your grade's a B plus, half your grade's a B minus, that probably, but doesn't necessarily mean that overall you'll get a B, because it's sort of based on the points, not necessarily the separate bits. The other little misconception people have is that people feel like, well, I've done all the quizzes, so I'm getting like 100%. That's like a perfect A on the quizzes. Well, that's true of most people in the class. So when you add up the points of everyone in the class at the end, it doesn't really help you. It sort of raises you the same amount as everyone else is raised by getting 100% on the quizzes. So don't count on the quizzes to save you, I guess is what I'm saying. Should expect that whatever you have other than the quizzes is probably about what you have with the quizzes. OK. Assuming you've pretty much done the quizzes. OK. Questions about midterm, grades, anything logistical that you want to talk about? Or anything on your mind? OK. Alrighty, so where we finished off before the midterm was doing probability. So we did, equally likely outcomes, complements, multiplication rule, addition rule, binomial formula. Where we're going now is, in a way, still sort of probability, but it's moving away from thinking about like the probability of event A or B or whatever, to thinking about sort of larger numbers of things. So the things that we did in chapters 13, 14, 15 are dealing with maybe a few draws from a deck of cards, or sort of relatively small number of die rolls, maybe 10 die rolls or fewer, coin tosses, things like that. Where we're going now, as we get chapter 16, 17, 18, is thinking about larger numbers of things, like 100 coin tosses. What do we expect to have happen? What can we say about probability in that context? Stuff like that. Okay, so that's where we're going, and I sort of view this part of the class as a little bit of a segue between this probability abstract setting of chapters 13, 14, 15, moving towards thinking about probability right now, but how does probability relate to real-world data analysis? So once we start in chapter 19 is sort of not very mathy, but once we start like chapter 20, 21, we'll start doing kind of data analysis things. And chapter 16, 17, 18 kind of provide the probability background or framework to talk about larger data sets. Okay, so that's sort of how you might think about what we're doing right now, is kind of in between those two settings. It's still kind of probability, but getting towards thinking about large numbers of like large data sets and things like that. Okay, so as a first example here, so this is chapter 16. As a first example, what I like to do is to think about coin tosses. So suppose I toss a coin 100 times and I get 99 heads. And I'm just going to interject here that I believe this is a fair coin, okay? So I toss a fair coin, equally likely to be heads or tails. This is very unusual, right? If you watched me flip a coin and you saw this happen, you'd think something was wrong, I think, on some level, probably. But suppose it actually happened. Suppose it actually happened that it is a fair coin, and then I got 99 heads. I'd like you to decide what you think. Actually, not what you think. I'd like you to tell me what you feel will probably happen next. And I would sort of like you to turn off the thinking part of your brain and just imagine it happening. And then, like, I stop and I got this kind of unusual result. And then, like, what does your sort of gut tell you is likely to happen next? Okay? So do you think more likely next toss will be heads or tails? And I will not allow you to say that they are equally likely. Okay? You have to pick either heads or tails. Okay? I'm going to make you vote. There's no right or wrong answer here. I just want you to sort of think about what your intuition says or your gut says about if this happens, what do you think is going to happen next? Okay, so who says they think heads is most likely to come up next? Okay, who says tails is most likely to come up next? Okay, so it's usually, when I ask this question, usually roughly half and half. Maybe a few more people said tails. Anyone want to say, like, what they're feeling that makes them say heads or tails? And I don't want really a mathy answer or anything. Anyone want to? Yeah.
Well, I think tails because, like, you get head so many times, there has to be one that just goes in the contrary.
Yeah, you've gotten heads so many, so this is pretty common, like, intuition behind it. You've gotten heads so many times that you sort of feel like tails are sort of due to come up next, right? Okay, yeah? So wait, which are you arguing in favor of? You think heads? Okay. So you're saying that this is so unlikely that it's not much more unlikely to get another head? Yeah. Okay. Yeah. Did you have?
Like, I guess after like 10 or 15, you expect tails, but then by the time you get to 99, you're like it's been heads so many times, you just expect another head.
Okay, so it's sort of a momentum kind of argument. He said sort of if maybe 10 or 15 times, he might expect tails to come up. But once it's happened this many times, he's like, oh, it's just going to keep happening, obviously, right? Okay, any other thoughts, comments? Okay, good. I'm sort of glad to see that people were able to think about this or, voice some intuition or feelings about this without saying, I don't think it's a fair coin anymore, right? So I think that's a common response, which is a little bit mathy, and I was hoping, you were able to not think about it in a mathy way. I think that real life, that probably happens to some people by this point. You think that I'm cheating or something's wrong with the coin tossing process, that you no longer believe this when you see this, which is fine. Like in real life, I think that's fine. But I did want to sort of get at this sort of intuitive idea. And how this relates to chapter 16. Chapter 16 talks about what's called the law of averages. Now, the law of averages kind of addresses what should happen in the future. Now, or I shouldn't say that. It addresses like what should happen in the long run. Okay. So a common, so I'll say the truth is if coin tosses are independent and it really is a fair coin, then should be equally likely. So let me write down a statement of the law of averages, and then I'll come back to this. So the law of averages has two parts, and the law of averages is sort of a general law that has to do with lots of different settings. I'm going to just describe the law of averages right now just in terms of coin tosses, and basically tell you what the law of averages says about coin tosses. So the way we sort of think about, or the way statisticians sort of think about this kind of a process of tossing a coin a bunch of times and then thinking about how many heads we get, is to sort of have this model in mind, that the number of heads we observe should be somewhere around half the number of tosses. But it's not going to be exact, right? We do expect to be off by, or we could be off by something. And that something we refer to as chance error. Okay? So what the law of averages says about this is that with a large number of tosses, the chance error will tend to be large in absolute terms. And I'll just sort of say as an aside, although small compared to the number of tosses. Okay, so some people find this surprising. I think a lot of people kind of, intuitively think that as you toss a coin a lot of times, you should get closer to what it is you expect. Okay, that idea is that somehow in the long run, things should sort of balance out. That you should get very close to 50% heads, 50% tails, and so the chance error should tend to be small. That's the second part of the law of averages, which I'll write down in a second. But in terms of the kind of just the raw number of heads, that's not true. In terms of the raw number of heads, as we toss the coin a lot of times, we should tend to get farther from half the number of tosses. Okay? So what do I mean by that? Well, if I toss the coin, just take a very extreme case. Say I just toss the coin twice. Okay? In 2 coin tosses, I should get around 1 head, half the number of tosses, and I might be off by a little bit, but I can't be off by very much, right? Most I could be off by is by 1, right? I could get 0 heads, I could get 2 heads, but I can't be off by very much. The chance error has to be small. If I toss the coin 100 times, sure, it's unlikely that I'm going to get 99 heads, but it's pretty plausible that I might get, 52, 55 heads, 47 heads. I might be off by 2, 3, 5, maybe. So the chance error in absolute terms, what I'm referring to is that kind of raw number of heads. So absolute terms refers to sort of 2 things. One is just kind of like raw number of heads. The other is in absolute value. So it's not that I tend to have a large chance error, meaning like it's always positive. Chance error could be negative. Negative chance error just means I got fewer heads than I expected to get. Okay? So in general, I tend to be farther. Now I might get exactly 50 heads out of 100 coin tosses. That would be chance error of 0. It could happen, but just if everyone in the class did it, everyone in the class tossed the coin 100 times, there's some variability, okay? And the chance error is that variability, and that will tend to be larger with 100 coin tosses than it would be with like 5 coin tosses, 10 coin tosses, some smaller number. Okay, any questions about this idea? Okay, so this last bit, although small compared to the number of tosses, that's what's telling us that 99 is not really likely, okay? 99 is really far, and it's far away compared to the number of tosses. Like it's sort of, yeah, so like off by, you know, maybe around 5 or so might happen. That's small compared to the number of tosses, but it's larger than I should expect for the chance error compared to some fewer number of tosses. Okay, so let me give you the second part. The second part is, I think, what most people that, I don't know, if you have any inkling of what the law of averages is about, it probably has to do with this part. And this part is talking about percentage terms. So the percent of times that I get heads should be somewhere around 50%, but it might be off, again, because of chance error. And this is often referred to as percent error. And by percent error, I just mean it's still chance error, but it's in percentage terms. It's just chance error. Chance error meaning that it's like random amount off. Okay, so percent error is what we will often refer to chance error in percentage terms as percent error. Okay, so now what the law of averages says about this is that with a large number of draws, the percent error will tend to be small. And just a little bit I'll add in on the end. Although it's unlikely to be 0. Okay, so this is sort of saying something related, but a little bit, you think about this in a little bit of a different way. In percentage terms, I should get close to 50% heads with lots of coin tosses. But again, I might be off by a little bit. The amount I'm off, though, should be pretty small in percentage terms. If I toss a coin 1,000,000 times, for example, I should get very, very close to 50% heads. I shouldn't be off by very much. Okay? If I toss the coin 10 times, if I get 4 heads out of 10 coin tosses, that's 40%. That's pretty far. That's 10% off. It would be really strange if I got 400,000 heads in 1,000,000 coin tosses. I don't know if it feels strange to you, but it would be unlikely. Whereas in 10 coin tosses, 40% heads would be quite easy to get. OK, so let me tie this in. Actually, any questions about either of these? OK, so I want to tie this in a little bit with this original example. So a lot of times people say something like, and someone said this, we've seen so many heads, somehow we're due to get tails. So there's this feeling sometimes that what this is saying is that in the long run, we expect to get 50% heads. So if we have 99 heads out of the first 100 coin tosses, it seems like, well, we need to get some extra tails in order for things to work out. So that, however, contradicts the idea that the coin tosses are independent. Somehow, if they're independent, what happened in the past shouldn't have any effect on the future coin tosses. So that seems like a little bit of a paradox to people. The reason why this works, the reason why the law of averages is true, is that we're talking about the long run percentage of heads. As you increase the number of draws, tosses. Draws is yeah, the idea of draws is something we'll get into later, but for now I'm just talking about coin tosses. With a large number of coin tosses, we should get closer to 50%. So the long run is really, really long, is one way to think about this. And whatever happens at the first 100 coin tosses, once I toss the coin 1,000,000 times or 1,000,000,000 times, this is sort of almost irrelevant what's happened here. It's going to get swamped by the fact that from now on, heads and tails are equally likely. I should get about 50% heads. And if I get 50% heads from now on, then this little blip of getting 99 heads out of 100 coin tosses is going to kind of disappear. Okay? If I get somewhere close to 500 million heads in the next billion coin tosses, this 99 extra, these extra heads, these extra 49 heads from the beginning is sort of irrelevant. Okay? It's going to get blown away by the long run behavior of the coin, which is that from now on we expect 50% heads. All right, so I just want to have people realize that that's, I think, a common misconception about the law of averages, that somehow it feels like this is saying that if one of them gets ahead, the other one has to catch up. Okay? It's not that the other one, typically the other one will sort of catch up in the sense that if we get 50% from now on, we'll kind of drift towards 50% overall. But we don't need extra tails after this happens. We just need 50% from now on. And then in the long run, we'll get 50% or very close to it. Okay? So questions about that? Any of this? Okay, so I think that these things come up for gamblers. If there are any gamblers out there, you should be aware of the psychological thing that might be going on for you, depending on how you answered. Both psychological things, I think, make people feel like they should keep gambling in some way. If they have lost and lost and lost, the people that answered tails, if they've lost and lost and lost, think, okay, surely I'm going to win now. I'm due to win. I've lost all these times. Now I must have some advantage. The people that have gotten heads, 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 and think that heads will continue, they have a tendency to continue gambling because they think they're doing really well and they should continue because they're on a hot streak. Okay? So both of these kind of psychological things are at play, I think, for different people. So depending on how you answered, you should maybe, if you ever do gamble, I'm not condoning it, I'm not advocating it, just saying, you should gamble wisely if you're going to gamble. And just be aware that these psychological things do sort of come into play, and people end up losing all their money at 4 in the morning or something. So. Okay. All right, so that's that bit about that. Okay, so I want to talk about some data. So this is this guy, John Carriage, is famous for no other reason other than he was imprisoned during World War II. He was a mathematician, and he spent his time in prison tossing coins and recording the results. So these are given in the book, and I'm just going to give you some of them. First 10 tosses, 100 tosses, 1,000 tosses, 10,000 tosses. And we haven't really talked about what I mean by expected anything, but it's fairly intuitive. We'll get into this more next chapter. When I say expected number of heads, I just mean half the number of coin tosses, just what you would expect to have happen. Okay? And then chance error. Okay, so this is exactly what I've written here. Number of heads should be about half the number of tosses plus chance error. So you can think of this, if you want, as this. Right? Number of heads should be somewhere around that, but off because of chance error. Okay, so his actual results, he got 4 heads out of 10 tosses, 44, 502, and 5,067. And what would he expect? In 10 coin tosses, he would expect 5. In 100, 50. In 1,000, he expects 500. And then expects 5,000 out of 10,000. Okay, so then what's the chance error in this first line? It's -1, right? 4 is equal to 5 minus 1. So essentially all this is saying is that he got 1 fewer head than he expected to get. Second line, he got 6 fewer than he expected. Third line, he got 2 extra. And last line, he got 67 extra. Okay, so what the law of averages is saying about this is that these numbers should tend to get larger. Okay, they don't absolutely have to. This third line, he got sort of unusually close to the expected value, or the expected number of heads. And I think that should even sort of look that way to you. You know, if you tossed a coin 1,000 times and you got 502 heads, you'd feel like, well, that's pretty close to 50%. That's maybe feels a little bit unusually close to 500 actually. I don't know if these other ones, you know, I don't know if 44 out of 100 feels weird to you or not. I don't know if 67 feels weird to you. Sorry, I don't know if 5,067 out of 10,000 would feel weird to you. None of them are like very unusual. It's not like 99 heads out of 100 coin tosses. But, you know, like I said, you expect to be off by a little bit. And the amount that you're off by should tend to get larger. Like I said, this third line is a little bit unusually close to what you'd expect. But you can see that, like, there's no way that these earlier ones are very likely. Like the first two, there's no way that you could be off by 67. It's just not possible, right? And the third one, that would, I think, seem pretty unusual. If your chance error was 67 in the third line, that would mean that you got 567 heads. I think would feel pretty unusual, you know? So anyway, that's what the first part of the law of averages says about Karacs's coin tosses. Questions, thoughts? Okay, so let's think about the second part of the law of averages. Percent heads should be around 50%, but might be off because of percent error. Okay, so this first line, 4 heads out of 10 coin tosses, that's 40%. And this column is a little bit silly. Just always 50% is what we'd expect to get. The second row, 44 out of 100, that's 44%. The third row, 50.2%. And the last row is 50.67. Okay? So the law of averages says about this that the percentage errors should tend to get smaller. Another way to say that is that these should tend to get closer to 50%. So what's going on here? The percent error here, 10% less than we'd expect, 6% less than we'd expect, 0.2% extra, and 0.67% extra. Okay, so we see again that these percent errors do follow the pattern that the law of averages, the second part of the law of averages says they should, except for this third row again. So this third row is unusually close to the expected value. So you might think of it as the exception that proves the rule, that there's this tendency, although sometimes it doesn't work. Okay, questions about that? Okay, so in your book shows some pictures of what's going on with Karacs's data. And I guess I'll just leave this. If anyone cares, there's this lecture series. So some pictures in your book you might check out. They're on page 275 and 276. So they basically show Karacs's data in more depth. Okay, so essentially they show a graph of chance error kind of tending to wiggle around a little bit, but basically tend to get larger, and percentage error wiggle around a little bit, but tend to get very close to 0. Okay, these percentage errors tend to get very small, and yeah, so the percentage of heads tends to get pretty close to 50% pretty fast, and then it sort of stays there, pretty close to 50%. Okay, so if you want, you can look at those. Let's see. Okay, so I have some true and false questions to ask you about this. So part of my motivation for asking you true-false questions is I'm hoping that people make a mistake, because I think it's a good way to learn, right? If you answer one wrong, then you tend to remember it. So yeah, so don't try too hard. So the first one is, oh, I'm sorry. The context for all of these is that I want to think about, I'm going to write down an event, and I want you to think about whether or not it's more likely with 10 coin tosses or 1 million. So I'm going to write down some events, and you can think about it. So I think one way to get yourself to make more mistakes is to not think too hard and to just sort of go with your gut kind of thing, right? And the reason why I want you to sort of do that and not like if you look at it and then you read the law of averages and you think about it hard and then you decide what you think, that you won't catch mistakes in your intuition that way. You know what I mean? If you just sort of look at the event I write and think, okay, is that going to be 10 or 1 million, and just sort of make a snap decision, you have an opportunity to find where your intuition is wrong. Does that make sense? And then you can kind of go back and think, well, why is my intuition wrong? What is going on with the law of averages? So that's how I think you might approach these. This is one of the few lectures where I'll ask you not to think very much. So the event I'm talking about is that the percentage of heads is more than 55%. Okay? So who says 10? Who says 1 million? Okay? So this is going to be really hard to do in 1 million coin tosses. It's sort of how I think about it. Is in 1 million coin tosses, you should be quite close to 50%. You sort of see what's happening here. 10, 100, 1,000, 10,000. So that's how I might think about how the law of averages is working, is that by the time I get to 1 million coin tosses, the percentage of heads should be very, very close to 50%. If it's very, very close to 50%, this does not happen. Okay? So it'll be a little bit easier to happen with 10 coin tosses. Okay, second one. Percent heads is equal to 50%. Okay, who says that's more likely with 10 tosses? Who says 1 million? Okay, so that's one that often people get wrong, and most of you did. This is going to be easier with 10 coin tosses to get exactly 50% heads. Okay? One way to see that, just in terms of what I wrote, if you trust me, is this. The percentage error is unlikely to be 0. So why is that? With lots and lots of coin tosses, with 1 million coin tosses, you are required to get exactly 500,000 heads in 1 million coin tosses. That particular event is pretty unlikely. it's likely that you would get close to 500,000. It's likely that the percentage of heads will be very close to 50%, but it's unlikely that you would hit 500,000 heads exactly out of 1,000,000 coin tosses. In 10 coin tosses, it's fairly likely that you would get exactly 5 heads in 10 coin tosses. It's not super likely. It turns out to be about a fourth of the time. If you toss 10 coins, you get exactly 5 heads about a fourth of the time. In 1,000,000 coin tosses, it's going to be very small because there are lots of things that are close to 500,000 heads that are not 500,000 heads. You get 500,000 in 1, 500,000 in 10, 499,992. There's lots of things that are close to it, but not exactly 50%. So if you're talking about exactly 50%, easier with fewer tosses. Okay? All right, let's just finish up here. Okay, so the event that the percentage of heads is more than 45%. Okay, so who thinks 10 tosses, 10 tosses, 1,000,000 tosses? Okay, didn't catch anyone, I don't think, on this one. This is 1,000,000. And yeah, so the reason is this, the logic behind it is essentially the same as the logic on the first one, that in 1,000,000 coin tosses, you should expect to get very, very close to 50%. And if you do, this will happen. You'll be more than 45%. Okay? So then, last one. Chance error is 2 or more. Is that more likely to happen with 10 or 1,000,000? 10? 10? And 1,000,000? OK. So most people said 1,000,000. It is 1,000,000. And this is the only one that has to do with the first part of the law of averages. All the other ones were in percentage terms. Large number of tosses, the chance error should tend to be large in absolute terms. So essentially what this is, what you might compare here is that chance error of 2 or more means 7 or more heads in 10 versus 500,002 in 1,000,000. Okay, so this is, I think this feels like not very far away from what you'd expect, right? 2 off in 1,000,000 coin tosses is just, it's very easy to be off by just a little bit like that. 7 or more heads, this is fairly unlikely, right? If I change this to like 3 or 4 or 5, then this is going to be much more unlikely, OK? If I change it to 6, it's impossible, right? It's impossible to be off by more than 6 in 10 coin tosses, whereas it could very easily be off by more than 6 in 1,000,000. OK, any questions about any of this? OK, so this part of the book deals with all this law of averages stuff. It's fairly intuitive. It's trying to sort of build your intuition behind what happens, what tends to happen with large numbers of coin tosses in this case. And like I said, this part of the book a little bit bridges this gap between thinking about probability and moving towards thinking about these kind of larger numbers of things and large data sets. OK? OK, so that's the book has some problems that are kind of this nature. And you'll see some of those. OK, but let's take a break. And then I'll finish up chapter 16. The end of chapter 16 sort of shifts into a different kind of topic. Okay, so like I said, the beginning of chapter 16 has to do with this law of averages stuff. The end of chapter 16, in some ways, I feel like belongs in the next chapter. It sort of goes with the stuff that's coming up more. So I think what I'll do is I'll talk about the end of chapter 16, but I'll also talk a little bit about chapter 17 as I go. The topic is what's called a box model. I'll say it this way. Box models provide an analogy. For chance processes which box models help to analyze chance variability. So the law of averages sort of tells us, roughly in some kind of casual way that chance error should tend to get larger here, and in percentage terms should tend to get smaller. But it might be nice to know how big. Is 67 bigger than we'd expect, smaller than we'd expect, about what we expect? So we'd sort of like to know, what if these tend to get bigger, how big do they tend to get? And box models sort of provide a way to get at that. Box models are somewhat particular to this book. If you look in other statistics books, they will approach this idea in different ways. I think the box model is sort of nice. It does give you this nice, concrete way to approach these problems. And I've mentioned before in this class that I think a lot of what we try to do in math and statistics is to try to make some problem that we've seen before, make some problem that we haven't seen before look like some problem that we have seen before. That's a lot of the idea behind the normal curve and using the normal table, is that we have some data set. Well, let's just put it in standard units, and if it looks like the normal curve, we can use the normal table and do all the stuff we usually do. And same thing with football-shaped scatter diagrams. If you get something that looks football-shaped, you can sort of just do this stuff and not care so much about the actual units or what the variables mean, and just think about it in terms of the same kinds of problems you've seen before. So that's, I think, part of why box models are useful, is that any chance process that we come across, or I shouldn't say any, but many chance processes will kind of naturally fit into this idea of a box model. And once you get it in the form of a box model, it makes it really easy to answer questions like, well, how big do we expect the chance error to be? What would we expect to have happen? Obviously, for coin tosses, it's pretty easy to tell what you should expect. Maybe not so clear what the chance error should be like, but box models basically get at both of these things. What should these things be? Okay, so let me start by just doing one, or I'll start by I'll write one more sentence. So for now, and by now I mean chapters 16 through 18. The analogy is something like this chance process, and by chance process it could be coin tosses, die rolls, something random going on. So this chance process is like drawing with replacement from a box of numbered tickets. And looking at the sum of the draws. Okay, so I'll start out with an example that's, I think, pretty obvious. Suppose I roll a die five times. So that's some sort of a chance process. There's something random going on there. And the way to think about that in terms of a box model is to try to make a box model that kind of mimics this. So it basically has the same properties as this. So if we roll a die, I should say add them and add up the die rolls. Add up rolls. So if we want to think about that in terms of a box model, what we do is we think about, well, what do we need to put in the box that will behave the same way as a die roll? So we have this box of numbered tickets. And if we have the tickets marked 1 through 6, that'll behave just like a die roll, one die roll. And then if we want to have something that will be like this, well, we might consider drawing 5 tickets out of that box with replacement. So every time you draw it, you put it back and mix them up again. And looking at the sum of the draws, so sum of the numbers on those 5 tickets. Okay? So this one I think is sort of clear in the sense that, this is just like a die roll. Pick a random number, 2, 1, and 6, and we're going to do it 5 times. This little arrow with the 5 means do it 5 times. This is supposed to represent a box with the numbered tickets. And you look at the sum of the draws, some of the numbers that are on those tickets. Okay, so one that's a little bit, any questions about that before I do another one? Okay, so then suppose I want to flip a coin, toss a coin 5 times. And count the number of heads. It's maybe not quite as clear how to translate that into a box model, like a box with numbered tickets on it. The way to do it is to think about, well, on each coin toss, there are 2 different things that could happen. I could get either heads or tails. If I get heads, then the number of heads I've gotten is 1, right? If I get tails, number of heads I've gotten is 0. So you can think about this as, it's as though the 1s represent the heads, the 0s represent the tails, and we're taking 5 draws from that box, okay? And adding up the results. So if you think about actual coin tosses, I don't know, tails, tails, heads, tails, heads, something. Number of heads is 2. If you think about the translation into a box model, what would happen is that the tails are like 0s, the 1s are like heads, and if you add them up, the sum of those numbers is 2. So, so that should be a 1. Okay. So if you think about just translating these possible outcomes, the heads and the tails, into numbers, and then adding them up, that's essentially what a box model does for you. And it's very common to have this kind of idea that if you're counting the number of times something happens, you have 1s for when that thing happens and 0s for when it doesn't happen. So any questions about that example? Okay, so I'll give you some sort of general instructions. So the first thing you want to think about when you make the model is what numbers go in the box. And I think that's usually the hardest thing to think about. What I try to think about when I want to try to make a box model for something that's a little bit weird is to think about what the quantity is that I'm interested in. So and what could happen to it on each draw. So I'll call that quantity of interest, the thing that I'm wondering about, what could happen to it on each draw. So in this first one with the die rolls, you're adding up a bunch of die rolls. On each die roll, the sum of the die rolls could go up by either 1, 2, 3, 4, 5, or 6. You know, whatever you roll, you add that amount to the sum of all the die rolls so far. So on each draw from this box, you want to add one of those numbers to the sum of the die rolls. For this, counting the number of heads, if you imagine what you would do if you actually flipped a coin, on each coin toss, the number of heads either goes up by 1 or it stays the same. So you either add 1 to the total number of heads so far, or you add 0 to the number of heads so far. So the quantity of interest is the total number of heads on each draw from the box, or on each coin toss, if you want to think about it that way. The number of heads either goes up by 1 or it goes up by 0. Okay? So that's one way to think about this part. What could happen to the quantity of interest on each draw? Okay? So second step is to think about how many of each number. So for the examples I did here, this is pretty straightforward because everything's equally likely. Fair die, the numbers 1, 2, 3, 4, 5, 6 are all equally likely. Fair coin, heads and tails are equally likely. Sometimes you get things where they're not equally likely, where, for example, if the coin lands heads 2/3 of the time, then you need to adjust things to make sure that the proportions come out right. So if the chance of getting heads is 2/3, you would want to have 2 1s and a 0. Okay? And the important thing to think about is what are the chances. So chances should come out right. For each draw. Okay, so again, you think, what's the chance of that? Well, in this case, it's 50%. So half the tickets in the box should be heads. Same thing for tails. But if it's not that, then you need to adjust. You need to add in more of one or the other or both to make things come out right. Okay, and the last thing is usually pretty obvious: how many draws? Okay, so for now, all the draws we do are always going to be with replacement. Okay, so I mentioned that up here, that we're talking about drawing with replacement from the box. Once we hit chapter 19, to some extent, and mostly in 20, we'll talk about what happens when your draws are they're without replacement. Okay, questions about those instructions? Okay, so I think, sometimes you will encounter boxes that are a little bit weird. So you get experience with it. And this is actually the idea of a box model, something we're going to use almost throughout the rest of the class in some form or another. Okay. So I talked about the idea of expected value kind of tangentially, and I'm now going into chapter 17. Chapter 16 basically tells us how to make box models, and chapter 17 tells us what to do with them. So you might notice this is a common theme through the book. Chapter 8, 9, we did correlation, scatter diagrams, and then in chapter 10, well, what do we do with them? We do regression, things like that. Okay. So here, once we set up the idea of box models, what do we do with them? I guess I just erased it, unfortunately. But in Karich's data, we expect to get half heads, right? So in 10 coin tosses, we expect to get 5 heads. In 100 coin tosses, we expect 50. Where does that come from? So first of all, let me just define expected value. So expected value intuitively is a long run average. Where did it go here? I mean, it really is what it says it is. It's the value we expect. So is intuitively the long run average. So you might remember when we first defined a probability, I talked about probability as a long run proportion or long run percent. So when I say the chance of getting heads is 50%, what I mean is if we toss the coin over and over again, in the long run we should get about 50% heads. So when I say long run average, what I mean is if you do something like this, roll a die 5 times, the expected value is, you might think of it as like if lots and lots of people each did this. So like everyone in the class rolls a die 5 times, and you write down all the results. Well, what do you think the average of all those results is going to be? That's what I mean by long run average. If you sort of do the whole thing over and over again, and then sort of what do you expect for that? So in 100 coin tosses, if I change this to 100 coin tosses, you should expect to get 50 heads, right? All right, so the formula for this, and I'll often abbreviate expected value EV. So EV for sum of draws from a box model is equal to the number of draws times the average of the box. When I say average of the box, I literally mean add up all the tickets in the box, divide by how many there are. Just take the average of those numbers. Okay. Okay. So for the first one of those, the die rolls. So I'll refer to that box. I'm not going to redraw it. The average of the box. Just add them all up. So 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. 21 over 6 is 3.5. So 3.5, and that sort of makes sense, right? Think about what average means. Intuitively, you can think of it as the balancing point, right? 3.5. So then expected value. So just as shorthand, sometimes I'll just write expected value. I'll usually write EV sum, meaning the expected value for the sum of the draws from a box is number of draws times the average of the box. So that's 17.5. So again, what that literally means is in the long run, if you rolled 5 dice or rolled a die 5 times over and over and over again and recorded the results, the average of all those should be pretty close to 17.5. Okay? Questions about that? Okay, so for the coin tosses, it's maybe even more transparent. Average of the box is 0 plus 1 over 2, or a half. And then EV sum is, I guess I just did 5 coin tosses again, so 5 times a half is 2.5. Okay. So you notice that this doesn't have to be a possible value. The expected value doesn't mean that you actually expect to get that value. It means that it's a kind of long run average, that sometimes you'll be above 2.5, sometimes you'll be below, but in the long run, you should expect, on average, you get about 2.5 heads in 5 coin tosses. Okay? So, and then you can see, if I just increase the number of coin tosses, this is just half the number of draws or half the number of coin tosses. Okay, yeah, question?
So 17.5 and 2.5 are the averages, I mean the percentage of you getting
it's not percentage, it's literally for the sum of the draws. If I add up the numbers in the box, or the numbers in the draws. So if I roll a die 5 times, you know, I didn't bring my dice, but if I roll a die 5 times, maybe I get 2, 6, 1, 1, 4. Okay? If I add those up, I get 2 plus 6 is 8, 9, 10, 14. Okay? So it's a little bit below what I would expect, right? And you can see maybe the numbers I picked are a little bit low. Right? So if everyone did it, then we should expect that on average, people would get around 17.5. Okay? So another question? Okay, so that is expected value. And I'm going to do standard error. So, like I said, expected value is like a long-run average. So there's a relationship between this expected value and the average in the sense that it's sort of like the center, right? The average is the center, expected value is the center. As we get into chapter 18, we'll talk about like the center of what. The average is the center of a histogram, balancing point of a histogram. Expected value has a similar interpretation, but it's not quite as concrete, because if you're talking about a histogram, you actually have numbers. You have numbers, you can take the average of them. The expected value, you don't necessarily ever roll any dice or flip any coins. It's sort of abstract and theoretical that I'm just saying, well, if I did do it, I should get around 17.5, right? And so, as we get into chapter 18, I'll explain that idea a little bit more, that it is the center of something, but it's not quite as concrete as the average being a balancing point of a histogram. Okay, so next idea is a standard error. And this is intuitively very similar to the idea of the standard deviation. The standard error measures the typical size of the chance error. Okay, so if you want to connect this to things we've done before, standard deviation measures the typical distance from the average, or the typical deviation from average, basically about how far do we expect to be from the average. RMS error is also sort of similar. RMS error tells us the typical size of a prediction error, which is in some sense like a chance error. It's something you might think of as sort of a random amount that we are off from what we expect. So in the same sort of way, standard error measures kind of roughly about how far off do we expect to be from what we expect. Okay? So if the standard error is small, that means that we should be quite close to the expected value. If standard error is large, that means that we should expect to be farther away. So chance error tends to be larger with more draws in absolute terms. And I'm talking about the standard error for the sum of draws, just like this is expected value for sum of draws. So as we add up the results from lots and lots of draws, like counting the number of heads in lots of coin tosses, we should expect the chance error to get larger. And the standard error reflects that. So standard error for sum of draws from a box is the square root of the number of draws times the SD of the box. Okay, so you can see as the number of draws gets larger, this is going to get larger. It's not going to get large as fast as the number of draws gets large. This square root kind of slows things down so that you don't expect to have a chance error of the same kind of order of magnitude or same just relative size as the number of draws. You expect to be relative to the square root of the number of draws. The SD of the box tells us something about how spread out the stuff in the box is, right? So, oh shoot, I erased those boxes, but the die roll box, 1, 2, 3, 4, 5, 6, those numbers in the box, the numbers in the box itself are more spread out than the numbers in just the 0, 1 for a coin toss. Okay, so this box is going to have a bigger SD, more variability. In both cases, I have 5 draws, but more variability in the case of the die roll. And this is literally just the SD of the actual tickets, the numbers on the actual tickets. OK, any questions on this? OK. So if you get back to when I originally defined box models, it probably seemed a little bit, I don't know, out of nowhere to sort of say this, and it's a little bit vague, whatever. I hope that it may be starting to sink in a little bit the point, right? We're making these box models in order to get a rough idea of what should we expect and how far off is it likely to be. Okay, so this gives us a rough idea of chance error. OK. So for that first example, the 5 die rolls, this is 1, 2, 3, 4, 5, 6, 5. OK. So I already got the expected value. Expected value is 17.5. And now the standard deviation of this box. You could do it, either of the SD formulas. I'll do it the summation formula. It's a little bit quicker. So 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. So this is the average of the squared values minus the average squared, average 3.5, and then square root of all that. So that's that second summation formula. OK, so 1 squared, 1, plus 4 is 5, plus 9 is 14, plus 16 is 30, plus 25 is 55, plus 36 is 91 over 6. And that comes out to be about 1.7. OK, and then standard error. I'll often write this standard error with, let me rewrite that. SE sum is square root of 5 times SD of the box, 1.7. And I'm sorry, I thought I had that calculated, but I left the piece of paper I calculated that on in my office. I think this is around 3.8. But if anyone wants to check that, they can. .8 something, I think. OK, so that tells you roughly, the likely size of the chance error. You expect to get around 17.5, but you might be off by, 3.5, 4 from that. Anyone do that? It's about 3.8? OK, thanks. And for 5 coin tosses, the box looks like this. 5 coin tosses. And we already got the expected value is 2.5. To get the standard error, we need the SD of this box. And again, I'll do that summation formula. 0 squared plus 1 squared over 2. So this is just the average of the squared values minus the average squared. Right, the average of this box is 1/2. And this comes out to be about 1/2, or exactly 1/2. Okay. It's, this is 1/2 here, right? 0 plus 1 over 2 is 1/2, minus 1/4 is 1/4. Square root of that is 1/2. So then SE for the sum of draws is square root of 5 times 0.5, which is about 1.16, I think, or something like that. 1.1 something. Okay. Okay. Oh, I'm sorry, it's more than that, isn't it? I'm sorry, I forgot my math here. What is that? That's, I guess about 1.2. Is that about right? 1.1? Okay. Should have left myself alone. Okay. Okay, so anyway, one point I wanted to make about this is just, again, to compare these, that because the SD is so much bigger to start with here, we get a bigger SE. And the second thing is to notice that, you know, as we increase the number of draws, we're going to increase the size of the standard error. I want to write down, before I let you go, I want to write down Karacz's data again real quick. And just tag on the standard error to show you that it is, you know, a measure of the likely size of the chance error. So number of tosses, number of heads, and I'll call this EV now, since I've already done it. Chance error. I'm going to whiz through this because I've already written it up. The interesting part is the standard error. Okay, that's the new part. So we got in 10 tosses and 100 tosses and 1,000 tosses and 10,000 tosses. He got 4, 44, 502, 5,067. You don't need to write this down if you want to just want to show you. This is the same as what I wrote before. Expected value is half the number of coin tosses for each case. Chance error is -1, -6, +2, +67. And now the SE calculation. Well, this first one comes out to be 1.58. This is square root of 10 times 1/2 is 1.58. And you can see it does pretty well. This is trying to give us the likely size of this, like roughly about how far off we would be. Seems pretty close. The next one is 5. This is square root of 100 times 1/2. So you can see that math. Square root of 100 is 10 times 1/2 is 5. And we're off by 6, right? 6 below. The next one is not so good, right? The standard error comes out to be 15.8, and we actually got 2. But, you know, just like with people or something, like you have some average height, some SD for height. Sometimes people are at the average for height. So this is kind of like that. This just happens to be a case where we got quite close to the expected number of heads. And then the last one comes out to be 50. So this is a little bit more than one standard error away, just like sometimes you'll see people more than one SD above average in height. Okay? So interpretation of expected value and standard error is very much like average and standard deviation. We'll get into that more in the coming lectures. One last thing I want to point out is this relationship here. You might have noticed 1.58 here, 15.8 here. The standard error goes up by 10 times here. The number of tosses goes up by 100 times. So that's because of this square root in the formula, right? Square root of the number of draws. When we increase the number of draws by 100 times, the SE goes up by 10 times. Same thing from the second row to the fourth row. Number of tosses goes up by 100 times, SE goes up by 10 times. Okay, all right. That's that. I'm about halfway through chapter 17. I've done the first 2 sections. We're going to skip the 3rd section. I'll do the last 2 sections on Tuesday and then get into 18. Okay?